Okay, good morning, everyone. Uh, I think we can say that the higher order differential equation finished. So I would like to start with a new chapter today, the Laplace transformation, and perhaps if we need some review and practice, I think we can do it maybe next week for the higher order, and also to prepare your quiz. And I think is the quiz will be next week? Is it okay, or maybe next 2 weeks? I mean, from everyone, if you agree, and we can set like between next week or next 2 weeks. Which one do you think? Same, only 1 hour Thursday. Do you think next week is good, or maybe next 2 weeks? That's December. Or both are okay. But I think a few expecting next 2 weeks. So do you think next 2 weeks is okay? I mean, it's up to your schedule. If you're feeling that, if you feel maybe it's also not good, then we can vote. Do you think quiz will be higher order? And because it's only 1 hour, perhaps I only prepare like 2 or 3 questions. Like if 2 means that the 2 will be considerably taking like a long time to write the answer. So do you think next week is good, or next 2 weeks? Next week, both okay. How about GDEP student? 2 weeks. Okay, 2 weeks. Okay, it's okay. 2 weeks. So I think now and then next week we are focused more on the Laplace transform. And maybe before the quiz, I prepare some review materials. And maybe from now, if I can prepare this week, maybe some exercise, I can choose some question I will pick from the textbook that perhaps it will be some like maybe I would like it will be simulation for your exam, and perhaps also in final exam, what kind of question that we expect. Okay, so I think we can move to our text. So let me write here, okay, just to make sure that we have taken notes that let me see the dates. So December 7, okay, December 7, or the
Will the finals get pushed back?
no, finals still the same. Because we are going to, like in December, we are focused more on the Laplace transform, and the final will include Laplace and the higher order.
When is the
Finals approximately around 19. Okay. So you have at least 1 week in between. Okay. So December 7 is quiz. Material is from higher order. And again, prepare A4 note, okay, 1 paper. All right. Now, before we begin the Laplace transform, I think we can start with just to make sure that we are agree. Okay, so if we have x squared like this, and we know that we can derive, we can integrate, right? If we derive, we sometimes using this, right? And we know that if we derive this become 2x. Okay, and if we integrate this x squared, let me write here, and maybe just integrate indefinitely with respect to the x. We get that this will be 1/3 x cubed plus a constant. Okay. And then if we maybe put some endpoints, like a number, then we can compute the exact value, right? And we've done this in pretty much in calculus when we derive and integrate, and we have several techniques that we also use in our class, right? So we call this, it's also a transformation, right? We call this a transformation. This is also transformation, in which, in our case now, we can also call this transformation as a property of a linear. So we call this linearity property. What does it mean is, basically, it can transform a linear combination of function. Okay, so let me write here. This means the linear property means transform of linear combination of functions is a linear combination of the transform. So if you get confused about this is actually if you maybe we can set some random function. For example, if we take derivative of, let's say we have a constant alpha and then a function of f, and then constant beta and then function of g, we can sort of transforming this into this, right? Alpha, beta is just a constant, and we can integrate these two notion, the function with respect to the x, and we can see that we can separate this and compute each one of them, right? So if you have a linear combination of functions inside here, it means that we can transform each one of them like this, right? So we can transform through the means of derivative, we can transform through the means of the integration. So the Laplace is another way to transform. Okay? So we are going to see what is the definition of Laplace and why it's so important for Laplace solving the differential equation. Okay? So we'll see that in differential equation we have several methods, right? We can have like from the linear, the first order linear, and then we have the higher order, and there are several methods, and depends on the condition, the requirements, we can set up like which one the method that we prefer to utilize. And now we have another method which actually requires a transformation. So basically, Laplace transform, the goal is to transform the differential equations into another equation that is easily to be solved, okay? Or you can say to be simplified, okay? And then we can find the solution easily, right? Okay, so basically, let me write here before we get into the definition. So basically, Laplace is, let's say we have an integration from a to b, and we have some function k as a function of s and t, and then we have f d dt. So basically the idea of this transformation or this integration here, okay, we are not yet into the definition of Laplace, but if we see that we could have like k and then we have also f. So what's happened when we have this? So if or maybe before here, maybe let me make something simple first to get into the idea of the k and f. So if we have 1, 2 integrations, and then you have 2x y squared dx, okay, you will see that we are going to integrate with respect to x, which we integrate the x only, if you remember the partials. And then we see that we can have this as, so 2 will be cancelled by the half, and then x will be x squared, and x squared will be 4 minus 1, which is 3. So we have, this is going to be 3y squared. So imagine that the x is here, and the other one, y, is t. But the result is, because we transform this integration with respect to x only, then we can expect the end result on the y. Okay? So when we have this, and imagine that this is x and this is y. So we can imagine that, or maybe we can imagine this this xt as x and y. So if we can relate this, then the answer is, this will transform this it means, let me write here. So it means transform function f of t into, let's say, a g of s, okay, or function with variable s. And that is what Laplace transform is. So we usually define the functions before, the original functions, as with variable t, and the expecting result, or the expected result, is in x. This is to make variable default variable. It actually can be any variable. It can be any variable, but to make our concept to be understood easily, we can set up from t to s. Okay? From t to s. So Laplace then we set the interval. So when interval from 0 and exactly at 0, and we increase the interval larger and larger, getting infinity, and we are going to see what's happened for a function to be in this interval. Okay? So it means that our interval in the integration, we are going to set, and we can take the limit using the improper integral. Okay? So basically, we set up a integration that is going to be from 0 to infinity for the k of this st f of t dt. Or if you remember the calculus, I think in calculus 1, right, we take the limit, and then let's say we have b, because usually we have t here, but t are going to be inside, so I will use another variable b. So this is going to be like infinity. This is from 0 to b, and then this will be k st, and then ft dt. Okay. And the expected result, the limit, exists, and then because it exists, and we can say that it's convergent, right? Well, if it doesn't exist, then it's diverged, and we don't have any meaning, right? So we are kind of interested on our k. So we need to select what function that is suitable. When we take the k here, it can be easily transforming the function of t become a function of x. Now I think because at the in the higher order, and I think from the first order, we can see that, or maybe in the higher order, we usually propose, especially when you have the linear constant method. If you remember that we have the second, we have the differential equation. For example, we have second order, like y double prime something. We can transform that into a quadratic equation, right? We can transform into quadratic equation. Remember that when we transform into quadratic equation, we propose that the solution will be in terms of function of exponent. Right? We have e. e with power of something, e with power of m something, right? So I think e will be the suitable case for our case, because if we have take e in function of st, you can see that somehow we can transform the f. Okay, so we propose that as our k. So let's k st, especially when we have e with power of negative st. And by using this, we are going to see some transformation that is really unique and special. We call it the Laplace transformation. So we define k as exponent, okay, e with power of negative st. So at the end of the day, I will take some conclusions first, and then we can see how it works. Okay. How to write Laplace transform? Basically, you have a function of, let's say, f of t, and you are going to write the symbol of Laplace like this, the unit curve L, like this, okay, like L like this. It means it's Laplace transform, and then inside the Laplace is the function that you want to transform. Okay. So again, why we want to transform this function? For what? What is our goal? Our goal is actually, like I said in the early introduction, is to simplify the differential equation and making it into like a polynomial, and then we can solve the polynomial. Okay. So we are going to set up this Laplace as this definition. So we can set improper integral from 0 to infinity of this e with power of negative st of the function t. Okay. So our goal is to transform this f. We transform this f into another function in variable s. Okay. So if this is converged, it means that it is the Laplace transform. Okay. And basically, this will be defined for all p positive. It means from the 0 to infinity interval. Okay. So basically, we can see and observe. Okay. After this, we can check some function of t. Okay. We can start from a constant and maybe start to see the linear, or maybe exponent, or maybe the trigonometric, what kind of response. So we can start from the idea of the basis on this introduction. Okay. So I think I can write later, and the next page you can okay, I think we can start to see some of the transformation. Okay, and then as a conclusion later, we can sum up what will be the shortcut. So if we want to transform, for example, Laplace of 1, okay, a constant, okay, it can be 1, 2, 3, anything. So if we have this, it means that this will be integration from 0 to infinity of e, and then the f now is a constant, so let me write this 1 like that, and dt. And this will be equal to, we take the improper integral. I hope if you remember what is that. If not, then go back to look and review your improper integral note. So basically we are taking limit, and then let's say we have b as a boundary, and then this is set up for 0 to b, and we have e negative st dt. Okay, remember we are going to integrate with respect to t, so we treat s as a constant. So integration of e, this will result, let me write limit b. So e is still e, but we are going to multiply with negative because we integrate. We multiply with negative 1 over s, right? So negative e, negative st, and then this is s. Okay. And then we evaluate from 0 to b. So if we plug in b, this will be, let me write here, limit b, and then this will be negative e, negative sb, and then negative negative, so plus 0 will be 1, right? And then over s. Remember, if we plug in the limit, it will be negative e, negative infinity, which means this will be 0, right? It will be 0 because it's 1 over e infinity. It will be 1 over something big, it's 0, right? In limit. So we can simply say that it will be 1 over s. So the Laplace of a constant, like in our case here, 1 is 1 over s. Which means if we have Laplace, let's say 3, this will be 3 over s. Okay. So one transformation. Okay. Maybe let me write some notes here. That limit, if we have x to infinity of e negative x, we can set up this as 1 over e x, which is 0. Okay, this is one example. So the integration itself in Laplace, is just a process in between. So at the end of the day, if you are using practically Laplace, you can just directly say this, the conclusion. So you don't need to like write one by one again. This is just a definition, and you can just use the conclusion as the final practice in your when you solve the problem using Laplace, you can just directly using this property. Okay, the next one is if we have let's say exponent. So Laplace of, let's say we have e with power of, let's say lambda t. Lambda is just a constant. Lambda is constant. So we set up the integration first, just to see what will be the conclusion. So e, remember, we write negative st as our transformation, and then the function that we want to transform is e lambda t dt. And because it's the same e, we can combine these two, and maybe we can take the limit, or maybe just combine first. This will be negative, and I will factorize negative t, so this will be s minus lambda, right? And then this will be dt. And then because seems too many in the power of the exponent, seems too many things. To integrate this, maybe we can substitute first to make it simplified in our observations, just to help you to see how it looks like. So let's substitute all this, the power. So negative t as negative lambda t. So we are going to derive. So this will be du, and the right side we are going to derive with respect. There's another t. We are going to derive with respect to t. So since s and lambda is non-t, so we are just writing the all together, and t will be 1, so this will be dt. So dt is negative 1 over s minus lambda du, which we are expecting this to sub this dt. Okay, and then this will be, let's take limit b to infinity, and then write, so e with power of u and dt will be 1 over, or here is negative in the front, okay, s minus lambda of du. Okay. So basically we can factorize the constant, which is the negative 1 over s minus lambda, and e with power of u is just e, so we can maybe, let me write a little bit to the left, and then this will be limit b, oh, why this is b, and this is, I think we can just take the e, u is this, so we can just write as it is, and then we plug in 0 to b, right? And basically we solve the limit. Okay, we solve the limit. So we start writing here. So plug in b, and then I will combine all together. So we plug in minus the 0, and then take the limit. Okay, so we plug in b to t, so this will be negative b, and remember that we have infinity here, it will be 0, right? So the first one is 0 minus the 0 here is just 1, so 0 minus 1, okay? So we can just see that this will be 0 minus 1, so which means that this is going to be canceling the negative sign, and we have this. Okay, so we can conclude that the Laplace of e lambda t, when lambda is a constant, is just 1 over s minus lambda. Okay. Or, example, if we have Laplace of, let's say 3t, like that, it will be 1 over s minus 3. Or if we have e negative 2t, this will be 1 over s minus minus, so it's s plus 2. Okay, I think one more for today's class is Laplace of a function t. Okay. Okay, let's try another one. Let's say if we have Laplace of t. So by definition, we write first the definition 0, infinity, e, negative st, and then t dt. Okay, we can write as a limit. And yeah, I think if you want to just integrate directly using the 0 to infinity, it's okay for just process, but at the end you can just take the limit at the end. Okay, it's okay. Although in like if you write to prove something, it's not okay, but just for calculations still okay. So take limit and then write that this will be or let me write t in the front just to see that we can have this. Okay. It's like we have x e with power of x, and remember that usually it will works with the integration by parts, right? Okay. So basically we need to solve these integrations. Like the variable is t, right? Variable is t, so it's like x, e, and then with negative x. So if that happens, usually you use the integration by parts, right? It's the most convenient process. So I will just using the DI method. I think I show you in the calculus. So let's say t and then e negative st we derive until 0. Integrate this, it will be negative over s, and then derive one more. Let me put here and there. So this will be e negative st, and then we have s squared, and we can multiply that and that. So this will be, let me write a limit. So we have negative t e negative st over s, plug in from 0 to b, plus or maybe negative, right? Negative e negative st over s squared, and then this is also taking from 0 to b. So let's write here limit b. This will be negative b e negative sb over s. Or maybe let me write this will be negative 0. And I think this one is 0, right? The whole thing is 0, right? And then negative e negative b s over s squared, and then this will be negative 1. And this part here, the e will be 0. So the final result is 1 over s squared. But to make our definition complete, this DI method, I will stop until, so I will not include the 0, and I will just make it into, so I will write like two alternatives. This is correct, but I will write in terms of, still we have the integration, or so let me write an alternative here for integrations is, so we have a limit b, let me write with the green, so negative t e negative st over s from 0 to b minus or plus here is 1 over s, and then still have integration of e negative st over s dt. Okay, we are going to see later that this pattern, okay, this pattern, the right side here, is actually the same thing as this one. But I'll write in terms of integration here, just to see that this one here will be repeated if we change the function, like t with power of n, or maybe we can see later t with power of 2, power of 3, power of 4. We're going to see this pattern a lot, and we can conclude something from there, but I think we don't have much time for that, so we can maybe later on the next week class. So maybe let me write some notes first, that here at least the Laplace of t is 1 over s squared. Okay, so if we have a linear function, 2x, 3x, 4x, you can write with multiplication of 1 over s squared. Okay, so let's say we have 2t, this will be 2 over s squared, okay, and so on and so forth. This is 0. So the next thing is to solve next week is Laplace of if we have a t with power of n. So let me write first what is the definition here. So we're going to solve this and see how it looks like. You can try at home. You can try if we have Laplace and then take t squared, and then if we have a t cubed, and then we can compare later with our conclusion when we have like power of n, what will happen. Okay, I think that's it for today. I would like to have a feedback question, just to see whether we have like common understanding in the higher order differential equation.